we have the Xreal Air ones here in our hands. Pretty old device at this point. It's been out at least 4 or 5 years. And the goal today is to really take a look at these, obviously from a product perspective. We're going to take a look, see how useful they are as AR glasses. But more importantly, I want to tear these down and take a look at the actual micro OLED panel that they're using from Sony and start digging around into the optical element. This little lens that you see here in front of what would otherwise be just a standard sunglass lens is actually a really complicated piece of engineering. It helps project the image directly to the user's eye via a polarizing beam splitter layer in the middle of the optical element, which we'll get to in a little bit. But for now, just putting them on, they obviously are not the most stylish sunglasses that you'll ever see in your life. It is going to be hard to call these true AR glasses. Obviously, they're meant more for gaming, more for consuming content while just sitting down. There's also the fundamental issue that I have to be tethered here. So I've got my Mac screen projected here. Sharpness is pretty good. The overall idea, though, is that you have multiple levels of brightness, and the max brightness, which I will say is really, really bright, is quoted to be about 400 nits to the user's eye. The overall weight, 79 grams, I will say it's not so much a problem in terms of the heft of the actual unit. It's more of the pressure that's being applied to the temples from this initial hinge design. And when we go into depth with some of the other devices that are coming out, both from Xreal, but some of the other brands on the market, I think this has become a solved problem where a much wider array of positions for the temple is in the quote-unquote comfort zone, where there's not enough pressure actually being put onto the user's head. The resolution, 1920 by 1080, 1080p, it's very, very crisp. I will say some of the sharpness loss that you might see when reading text on this is actually probably due to the optical architecture that's being used and that we're going to be talking about. The refresh rate, again, no issues there. We have a minimum 90 hertz and up to 120 in 2D mode. I would say very, very easy to notice that there is sufficiently high resolution not to cause that tearing effect that you might see in lower resolution displays. There's obviously intrinsic screen mirroring that can happen through the USB-C cable that's included. This just becomes a second screen for any device that you plug this into. There is no 3 degree of freedom head tracking native to the headset. You will have to get used to the concept that your screen is now fully fixed to your gaze, and specifically to your head position, actually. Your gaze can shift across the entire field of view, but the micro motions of your head, just while you're sitting down, are going to be quite noticeable in the fact that the screen is jittering around you, which is not very typical of a screen that you use. And as a monitor replacement, this is unlikely to be convincing to many people because of the fact that there is no 3DOF tracking native to the device. The other inputs that we have are just the screen on and screen off. So you can see now I turned off the screen and turn the screen back on at full brightness. Again, quite bright, so we're gonna notch that down. I definitely see minimal issue in a office environment to be able to use this at an intermediate brightness. Overall, a pretty good first entry into the head-mounted smart glass realm, but we'll dive a little bit deeper into the hardware here. We'll say the level of reassembly that I can expect out of this is probably quite minor, but that is something that we'll only know when we try to put it back together. You can see that the glue up top here is starting to separate. We can try and speed that along. And remove the clips from the top. Quite a strong bracket here, protecting all of the delicate optical elements, as well as a proximity sensor and a few other components. Again, take a look at Jerry Rig Everything's video to go further into detail on the audio components and the way that we get power to this unit, since it has no onboard battery. What we're going to be focusing on primarily is the optical elements here. And so we'll need to remove these Phillips screws that are holding in place the aluminum bracket that serves as the heat sink of our material, or of our display as well. And so let's get to it. Okay, so you also have to remove the screw that connects the stems to the main lenses of the frame, and then there are further 2 screws right underneath that actually ultimately connect the aluminum assembly to the plastic frame. And so with these 2 screws, plus 1, 2, 3, 4 other screws, we can finally start removing the aluminum assembly off of the actual plastic element. So at this point, we have what we see here, which is our 2 main stocks connected to the main assembly. Again, I want to make sure that these are still functional, because the microdisplay essentially requires power via the USB-C input here. Sure enough, we are still able to power on at least the left eye. Take a look here. So this is good news. We'll be able to take some brightness measurements once the optical element is actually taken apart. Okay, so it does look like we have the ability to power these on without the proximity sensor. So for now, take a look at this guy and put him to the side. You can see here that if I zoom in, we do have power here. Unfortunately, you can't see it very, very well, but that's just, there you go. See, that's the left eye element and the right eye optical module. So we have both microOLEDs functioning through the main logic board, and now it's just a matter of taking apart the optical module. So again, the optical module is going to be our display module plus our lens module bonded together. This is what's referred to as an optical module. We're going to take this apart, take a look at the lens just by itself, and then take a look at the OLED, the microOLED display powered on. So our optical module holds the microOLED panel that we see at the top here with the thermal paste that was connecting to the aluminum heatsink. It holds this in place essentially by the 2 glue lines that we have on either long edge of the panel. This is bonding it to this plastic frame that gives a very precise distance between the actual display. So this is just a plane that is projected through a series of lenses. And we'll take a look at all of these lenses later. But the idea is, if we cut that glue line, and you can see here some further glue here between the flex cable and the inlet to the microLED panel. If we cut those off, being careful not to sever anything, we should be able to get a nice individual microLED panel. So now with this unit taken apart, we can actually plug in the power back to the device and see if we get power to the OLED panel. And if everything went right, we can. So we'll take a look at the detailed optical path later, but just as a little sneak peek, we can take a look at the image. We've got here a single optical module from the Xreal Air 1. Again, this is with the display module at the very top, including the PCB that helps drive our display, connected to the plastic housing that connects the display module and the lens module, which includes quite a few different lenses. So we'll break these down one by one and take a look at each individual component. So now that we've broken down the optical module into the various components, we can go into what each of these are and what they do. Very first thing we see here on the far left is the actual display module. So the display module consisted of obviously the OLED micro display, as well as a couple of other components like the flex cable. And what we saw a little bit earlier overhanging from the module was this optical film at the very top. This is essentially our initial polarization state film that defines how we take the unpolarized light that's coming out of the OLED microdisplay and convert it into a known polarization state that we can ultimately do something with inside the rest of these elements. So this is a combination of a linear polarizer as well as a quarter wave plate, which essentially serves to change the polarization state to what's known as circular polarization and allows us to more effectively bounce the light within the rest of the optical element without having too much loss by playing with just linear polarization. And so this initial film is laminated to the top of the OLED microdisplay, which produces our unpolarized light and helps provide circular polarization to the light as it goes through the next lens element that we see here. This lens element is a simple transmissive A-sphere. It doesn't actually change the polarization state at all, but it does help magnify the image that's initially generated on our flat panel display. This image goes through the lens and widens and distorts that we will have to correct later before we deliver the image to the user's eye. But this is sitting on top of the OLED microdisplay and the linear polarizer plus quarter wave film that we have. The next component is our barrel or our lens housing. This is a single piece of injected molded plastic that ultimately defines the distance between the display and all of the critical optical surfaces, like our reflective polarizer and half mirror that we'll talk about later. This housing actually provides the critical mechanical tolerance that you can achieve and how close you can get the planes of all of your images or all of your rays to the ideal design that you've put on paper. In practice, realistically, you will have to make some sacrifices because no tool is perfect, and we're going to get some distortion in the injection molded plastic that's going to give us a few microns or a few tens of microns of inaccuracy from part to part. But once we've assembled the lens and OLED microdisplay into the housing, we can start looking at the lenses that actually start bouncing light. And so we have our first lens element here. It's a flat lens that goes onto this 45-degree surface. And this is what we refer to as a polarizing beam splitter sometimes, but really we're talking about a very interesting functionality here, which is, you can see I've removed the film from the lens here. On the bottom side here, we still have the film laminated to the lens, but on the top side, we've actually removed the film, which is a two-component film. At the top right, a quarter wave plate, and below it, a reflective polarizer. So remember, we started off with circularly polarized light from the display that has had its circular polarizer laminated to it. We now enter and magnify the image and go to this first surface where we take that circular polarization and turn it back into a linear polarization state once we pass through the quarter wave plate. As we pass through the quarter wave plate and linearize our light again, we can reflect off of what's known as a reflective polarizer. Typical polarizers are absorptive. They will generally absorb light that is of the wrong polarization state and transmit light of the correct polarization state. But for a reflective polarizer, instead of absorbing a light of incorrect polarization state, it will fully reflect it. And that's key to allowing us to do what we are doing here and folding the image in our birdbath optic. So once the image has been reflected here from our reflective polarizer, it goes back through the quarter wave plate, circularizing the polarization state again, and it will then go to our next optical element, our final unique element, which is the half mirror. This is a PVD coating, a physical vapor deposition coating, that actually it provides some really unique functionality. And that is that it can perfectly reflect or transmit at a fixed ratio the both vertical and horizontal polarization states that we are creating within our element. And what that allows us to do actually when we send circularly polarized light incident to the surface is to flip the circularity. So let's say we had a right-hand circular polarization that came out of this quarter wave plate. When it hits this half mirror, it will change to left-hand circular polarization. And when you change this circularity, if you go back through the quarter wave plate, what you're going to get is a linear polarization that is 90 degrees from when you started from the reflective polarizer, aka the light can now fully pass through the reflective polarizer because it has been turned so that the reflective polarizer will transmit it. And that is ultimately the light that we get back to our eye. So this birdbath optic, or folded optics, as some people might know, is really key to enabling a much longer focal path for the light that's coming out of a display, and really allowing us to magnify that image from what is otherwise a less than 1-inch display to what you see in this optical element, which is a 200 plus inch display. We've now put the unit back together, and we can actually see if it functions as intended when the headset is worn. We're not going to have a better looking pair of glasses compared to when we started, but we do still have functional microdisplays on both the left and the right eye. Right eye, you can see that we still have the optical element in place, having the projection to the user side as well as the reflection through to the world. And then if we take a look, we do have, with a little bit of proximity sensor coverage, the ability to see the microdisplay in the left eye. And this is essentially the full 5000 nit display that Sony sells as a flat panel that we then integrate through our optical element, and through all the various optical losses is where we can get around 400 nits total delivered to the user's eye. There's a lot of inefficiency, obviously, in this design, and we have to take it as is because of the nature of the birdbath optics and the reflection optics that or the reflection paths that we have to use to magnify the focal length of the system. By design, actually loses quite a bit of light throughout the system. However, this is a great first attempt at user consumer AR glasses. Again, whether we agree on whether or not these are true augmented reality glasses is still to be seen, but what is possible to see is your laptop screen. So with that, thanks for watching DTC's teardown video of the Xreal Air 1